Hello everyone, my name is Zheyuan and I'm a PhD student in Core Robotics Lab. Multi-robot systems are increasingly being adopted in various environments. In this paper, we focus on the problem of multi-robot task allocation and scheduling with application in final assembly manufacturing. To achieve an optimal schedule for a user-specific objective, the robots must be allocated with a proper number of tasks and process these tasks with optimal order. Key challenges are, first, we have temporal constraints on task completion and their relationships to be satisfied. We also have spatial constraints, which in turn creates intercoupled disjunctive time window constraints. Traditionally, this problem can be formulated into mixed integer linear programming and tackled with exact solvers, which can find optimal schedule. But they are computationally expensive and can't generalize to large-scale problems. On the other hand, there are application-specific heuristics that are lightweight and effective. However, they require an army of consultant and domain experts to develop, which is still quite expensive. With recent breakthroughs brought by deep learning, can it be used to save the day? Promising progress has been made towards learning heuristics for combinatorial optimization problems. However, multi-robot scheduling has more complex graph structure, and thus better model and better learning is needed. We propose ScheduleNet to serve this end. We formalize the problem as constructing the schedule as a Markov decision process, and then greatest policies that generate schedules by appending tasks to an individual robot's partial schedule based on a score queue function approximate with the neural network. Simple temporal networks are ubiquitous in modeling multi-robot task allocation and scheduling problems. Exploring the fact that task duration is deterministic, we remove task finish time nodes during STM preprocessing to reduce the graph size. We first extend the simplified STM by adding robot and location nodes and edges describing their relationship. We also add a state summary node and Q values nodes to directly estimate the Q values. We generate initial input features based on the partial schedules of the current state and develop a building block layer that learns per edge type message passing, followed by per node type feature reduction. It also utilizes attention mechanism. This is the meta graph showing all the node types and edge types. We also gave an example here consisting of 19 task nodes, 2 robots, 2 locations, and several Q-value nodes. Due to the large search space of scheduling problems and most of the permutations of the tasks are infeasible, Q-learning algorithm is not effective. Moreover, it is practical to optimally solve small-scale problems with exact method. Given the scalability of the graph, we expect that exploring such data to train ScheduleNet can generalize well towards solving unseen problems, even in a larger scale. We define expert laws to learn from the expert actions, and alternative laws to ground the remaining Q values using offset. Combine the two with L2 regularization gives the full supervised loss. For experimental results, we use randomly generated problems simulating multi-agent construction of a large workpiece. The matrix we use is percentage of problems solved with an optimality ratio, and we benchmark against 4 different algorithms. Experimental results show that ScheduleNet model significantly outperformed EDF, tertial, and homogeneous graph, and were consistent through solving medium and large problems. For some of the large problems, the solution found by ScheduleNet had better make spans than those found by Groovy under its cutoff time, and the performance of ScheduleNet scaled up to 200 tasks, 10 robots, and 10 locations with an affordable increase in computation time. Besides makespan, we also evaluate ScheduleNet towards optimizing a different objective function to show its generalization capability. Thanks for your attention.